thanks for organizing of this conference. I learned a lot, and thanks for giving me the chance to introduce the work finished when I'm a PhD student in cooperation with Li and so on. And as we can see in the title, I try to give constraints on EDGB gravity, which is a subset of ESGB. And with this event, 1908-14, I found dark matter and the neutron star more popular in this conference. Sorry for that. I didn't focus on dark matter and the neutron star. Maybe I will focus on them later. So as you can see, up to now, like work I detected about 100 events, gravitational wave events, and about 90% of them are black hole binary events. So that's the reason I focus on binary black hole. And the event of 1908-14 is special due to the evidence of processing and higher harmonics with a larger mass ratio about 10. Here I take 15114 as an example to show the string of these events of binary black holes. As we can see, the waveform model, gravitational waveform can be described and can be divided into 3 parts: inspiral, modular, and rain down. This stage between inspiral and modular is called intermediate region. And for inspiral and rain down, these two regions can be described by, it can be described analytically. And for inspiral, it's described by post-Newtonian theory. And for rain down stage, it's described by perturbation theory. And for modular stage, we can only start it with NR simulation due to the strong field. And for the EDGB gravity, it's special, and it has been interested in press speakers. One can study the effects of the coupling constant introduced by this gravity with different methods. For example, NR simulations and the PPE framework. The later one is an analytical method, and for the NR simulation, one can study the effects with a larger space of coupling constant. With the PPE framework, one have to assume that the effects of the coupling constants can be ignored, and we describe the effects with perturbation theory. And here I show the waveform model of the binary black hole event. The A means the amplitude and the phi is the phase. For the GR case, the phi is in this form. TC means Johnson time, phi C means reference phase, and here phi is a phase in different post-Newtonian order. And for the modification given by different modified gravity theories, they have different form, and we only consider a leading order of the modification given by different theories. And here is some other parameters. Then for EDGB gravity, it introduces an additional parameter scalar charge, and what we want to constrain is the coupling constant alpha. And the modification on the phase of the gravitational wave is writing in this form. It's quite simple. And it really is a function of masses and spins. Before our work, there is a work give constraints on this theory with gravitational wave events from GW190412&GW190814-Dr. And this work is also an important reference of our work. They give constraints on the alpha with these two events, and here we can see the constraints on alpha is about 5 0.6 at 90% credibility level. And they give these constraints directly from the posterior of delta phi mass 2. This is the posterior of this parameter is published by Lego, and also with posterior of eta is symmetric mass ratio of these events. Then they calculate the posterior of alpha. Alpha is a function. Beta is a function of alpha. Then actually there are, if we want to get the posterior of alpha, there are several different methods. For example, we can calculate the posterior directly from the relation between alpha and delta phi and masses and spins. And also we can use other methods, for example, rating method and the Bayes method. Bayes is we need to do more calculations because it's slower than these two methods. So another method is rating. We will introduce later here. For the rating method, if we calculate the posterior of alpha directly from the relation between theta 1 prime and theta 1, it means we assume the prior non-uniform prior on on squared alpha. Because if we assume uniform prior on delta phi and masses spins, we can calculate the distribution of squared alpha directly, and we find the distribution is non-uniform. But what we want is a posterior based on a uniform prior like this, like a red histogram. So what we need to do is rewrite according to these two different priors. And for the distribution, for the posterior density larger than the prior one, we should give a larger weight. And for the prior two, for the region where the prior two is smaller than the prior one, we give it a lower weight. Then we can rewrite posterior according to this weight. Then we can get the posterior of the reweighting method. Then for the another method is a Bayes method. So it's according to the Bayes inference. And what we want is a posterior of alpha, and we have the prior of different parameters, and the important one is likelihood. To get the likelihood, we define the inner product between different signals, or between like this. Yeah, then we can calculate the likelihood. So we also need to get we need to estimate the noise from the raw data of the events around the events. We need to estimate. For here, I take 15914 as an example. We should perform a high-pass filter on the raw data to make the noise more like a Gaussian noise. And then we estimate the power spectral densities of these events with a Welch method, the thermal writing like this. Then here I show the results of the reweighting method. As you can see, the blue dashed line means it's given by the constraints, given by the threshold of perturbation theory. The region lower than the line means it's reasonable, and the parameter the effects of of squared alpha can be taken as perturbation. The region after this line means it cannot be taken as perturbation, and if the dispersion is is larger than this line, it means it's unreasonable. So as we can see, the reweighting method gave reasonable constraints. Then here I show the results of the Bayesian method, and as you can see, the Bayes method give more reasonable constraints on this theory. For the relative method, the wide space between the distribution and zero may lead to an unreliable conclusion that there is a derivation from GR, but that's not what we expect. And for the Bayes method, there is no such feature. So, and finally, we give the constraints from Bayes inference on 1908-14. The best constraints is given by PVC HM waveform model. The constraint is 0.38 kilometers. Then here I summary with recent studies based on different observations. For example, here is a study based on X-ray and also previous studies based on these events and a recent study based on 1908-14. They upgrade the method we adopt here and give a better constraints of about 0.23 kilometers on squared alpha. So here is a brief summary of my talks. Thank you.
Thank you very much. Other questions for our speaker? If not, then I will start. I have a more technical question, I would say. Okay. If I understood correctly, you do not use the LIGO software LaSuit, right, for the analysis of the event?
Sorry.
So there is a LIGO software for analyzing the data.
Software?
Yeah, from the LIGO collaboration. So you use your own software to analyze the data.
Sorry, I didn't mention that. Software I use the Belby and PyCBC.
Yes, PyCBC?
Yeah.
So this is what you used as well?
The most important software is Belby. PyCBC just do some basic conversion between parameters.
Mm-hmm.
And also the sample I thought is PyMartinez. Yeah.
Okay.
Okay. Thank you.
Yeah, this answers my question. Thank you. Wait a second. Are there more questions? Are there more questions for our speaker? This doesn't seem to be the case, so thank you very much for the great talk.